we were talking about the important features of linear regression. So let's start working with some real data points. So here I made these two arrays, an X array and a Y array. So if we see this as a scatter plot, we can see the points here. And we can see that there's kind of a linear trend, but we don't know the exact line that goes through it. So this is when we would start using our linear regression. In order to find the slope and intercept of the data, we need to first find the correlation of the data. But that's very hard when we're working with two different data sets with two different units of measurement, because here we see that height has an inches unit, but weight has a pounds unit. So how are we going to find the correlation between these two when we don't have the same units across both of them? And this is why we start using standard units. And standard units is a unitless measurement of how far a data point is from the mean of the entire data set. And it's meant to point different units of observation onto the same scale. It uses mean as the center point and uses standard deviation as a distance. So each point within the data set has its own number in standard units. So here, let's work with just the Y, for example. The X, sorry. So if we have an X, we want to subtract the mean from it. So we would do np.mean of all of X, and then divided by the distance, because that's how many standard deviations it is away from the mean. So here we have an array of negative 1.16. So 1 is negative 1.16 standard deviations from the mean of X. And it goes along, this formula applies for each point in the data set. So now let's code a formula, a method, so that it's easier to apply across all things. So let's say we have something called data. So we want to apply the same exact formula. So it'd be data minus np.mean of data divided by the standard deviation of data. So if we run that and we just run standard units on X, we get the same exact array because it's the same output. And if you notice something interesting about standard units is if you add all of these back up, standard units of X, you get a value which is very close to 0. And it should actually just be 0, so that there's some computing error. But if you notice, if you add everything up, it becomes 0, because for every point that causes something to be dragged all the way here, there's another point that'll balance it out on the other side. So now that we found the standard unit of our data set, we can find so here, you can see the standard unit formula again. So now you can find the correlation. And correlation is referred to as the correlation coefficient R. So it measures the linear correlation between two variables. And this coefficient R is always a number between -1 and 1. So 1 refers to a perfectly positive linear relationship, and you'll see some examples. And -1 refers to a perfectly negative linear relationship. So here is a positive correlation. So you would expect an R value between 0 and 1, probably closer to the 1. And -1, this would be closer to a -1 value for R, and no correlation would be very close to 0. So in order to calculate correlation, it would just be the mean of running standard units on X multiplied by running standard units Y. So here we see the correlation of these data points is very close to 1. So you can see just from that number alone, it tells you that these data sets are very linearly correlated. So now if we just run this back in here, now we have a method for it, and let's define it. So if we run correlation on X and Y, we get the same exact output. So now that we found, it's the average of the product of two variables, right? So the two variables have been put into standard units, and then we multiply them and we find the average. And the variables must be in standard units. It will not work if it's not in standard units. So now in order to calculate slope from the correlation coefficient, it's just the correlation coefficient multiplied by the standard deviation, the standard deviation of Y over the standard deviation of X. So now let's code that. So it would be R, which we have over there. So it would be correlation of X and Y multiplied by the standard deviation of Y over the standard deviation of X. And this makes sense because normally when you're calculating slope, it would be rise over run, right? So change in the y over change in the x. And the standard deviation measures the variance of the y, and then it measures the variance of x. So it's change in y over change in x. And you multiply that by the correlation coefficient. So now let's write a method for that again. So it would just be the correlation of x and y multiplied, I'll just copy it. That. So now if we run slope on x and y, we see that the slope is very close to 1. So we can kind of imagine a slope of 1 just going through here right now. All right, so the last step is intercept now. So this is our basic formula here. Y equals the slope times x plus the intercept. So in order to find intercept, you basically substitute and solve backwards. So y is the mean of all y values. So you could use np.mean there. And x is the mean of all x values. So another np.mean. And slope, we just calculated the slope. So now we just plug everything back in. Intercept would be the np.mean of y. And then you subtract it over. So it would be minus np.mean of x times the slope of x comma y. So now if we call intercept, we get that this is our intercept point. Nice. So if we just copy paste this here and we run intercept on our data points above, we get the same exact value. So now let's just put this into an array here. So the first value is our slope, which we calculated right here. And then the second value is our intercept. So now if we want to graph all that again and see our line across our data points, we can go ahead and write slope intercept. Variable name, data x. So here we have our line going through our slopes, and this line very closely resembles our data.